So good morning. So Ashish, you'll be glad to hear I'm not going to talk about apps. So we've seen and heard a lot of talk about apps over the last couple of years. And what we've seen, at least in Mentor, is that apps, or the usage of apps has increased. And this is actually starting to drive renewed interest in property checking now in our customers. So with the birth of this new interest, or rebirth, if you like, of formal property checking, there's a lot of users out there with probably less experience than many of you in the room. So there's some more novice users. So what we thought we'd do is cover some of the basics, some good guidelines, if you like, for using property checking, and take things back to basics a little bit. So before we do that, just a couple of slides on some trends, some facts that we see or have seen. So this is out of the Mentor stroke Wilson Research Group study from 2012. The 2014 data is going to be presented at DAC this year. So if you're there, you can check that out. But what this is trying to show you is formal, and this is formal in general, is used across all designs. So echoing some of what Ashish was saying earlier. So we see, small designs right through, and obviously the bigger designs, the more complex designs will use more formal. So this is not just property checking. There's obviously apps mixed in with this as well. But just to show, there's not one design or one style of design, if you like, that is suitable or using formal out there. Second is usage. So there's two primary formal usage that get talked about: bug hunting and assurance. So this is a graph here of bugs found against time. So the time is from rev 0 of the RTL, so early stages, right through to tape out. So you can use formal very early to do bug hunting. So as soon as you have some stable-ish RTL, you can create some properties and start bug hunting there. Assurance typically pays dividends later on. You need more stable designs, and this is really where you're trying to prove something against a specification. What's interesting here, though, is that we still see usage across bug hunting and both assurance as well. But with the birth of the apps, many of them are actually focused around the assurance kind of phase. So connectivity checking, register checking, for example. These are spec-driven verification challenges. So they're really in the assurance space. So actually, assurance used to be the kind of domain of the expert. Required more formal expertise typically, but we're seeing some of the apps play there as well. And so the spread here is across both of these techniques. And the final one here: who writes assertions and who runs formal, in fact? And we're seeing that still there's a trend to both. Actually, the market and the usage of formal is spreading. Again, partly driven by apps, but model checking too. So the design engineer is able to run formal, both for bug hunting, but things like the auto checking, coverage checking kind of tools, and the verification engineer is still predominantly focused around potentially spec driven checks. But we're seeing the wide range of usage across both. So let's talk a little bit about these right ways. So as I said, we're seeing this resurgence in formal. So we wanted to talk about some foundations here. So the first thing is a test plan, a formal test plan. If you're going to succeed in formal, we mandate that you write a test plan for formal. You understand what you're going to do with formal, where it's going to be applied, where you're going to share formal and simulation resource, and so on. Who's going to do the work, and where is it going to be focused? And the test plan is built along our 4 pillars here. So we have design style, and we're going to talk about these 4 pillars in a little bit more detail. Design style, assertions, formal engines, and finally coverage. And so a good test plan has these pillars underpinning it, and then of course it's based on your infrastructure as well. So let's talk about design style. So firstly, the wrong way. So again, Ashish touched on some of this, so our presentations are somewhat in sync, I think. But running formal on the SoC, it's typically a no-no. You're not going to run formal on every part of the SoC, but certainly areas of the SoC will be well suited. And things like connectivity checking will be ran at the SoC level, and you perform some abstractions there to help things along. But typically, you wouldn't focus on the SoC, so this would be the wrong way. You don't want to run formal on a block you know nothing about. So you need to know something about the block. You need to know how it works. You need a very good specification. Or in the absence of a good specification, you at least need to have access to the designer who wrote the block and good access as well. You're going to find bugs. You're not going to be able to debug if you don't know what the block's meant to do or have the guy or girl there to help you debug this. Again, running Formula on a block without a proper design spec. So a design spec, but a good design spec. You need a detailed design spec. You don't want to be coding properties by reading the RTL. Your properties are going to be way too implementation focused. You need to push back up, and we'll touch on this again later. But you need to write properties and verify from the spec, not from the implementation. And data transform. So data transform is typically not the place you want to focus formal. So floating point, MPEG decoders, those kind of things. Typically, they're out of the reach of formal tools, and most people that are trying to use formal. Sure, model check. I'm talking about model checking here. It's probably checking. So the right way, so specifications we talked about, design and interface. So you have your design spec. Equally important is the interface specification. You need to know how to constrain this design. You need to know what the interface does, how it works, or how it should work, so you can write constraints so you can get the verification done. Control logic is typically the sweet spot for property checking, for model checking, and this would be, you know, your first target probably. But data transportation can be good as well. So link layers, that kind of thing. So we have some examples here. There's a recommendation here. If you have access to it, then you've got a block you're running formal on. We would suggest that you run autoformal or the coverage formal checking type apps as well. These will give you an indication very easily of how controllable or observable your design is. They'll show up areas of the design, the block that you're trying to verify that are hard to reach, hard to control, hard to observe. And so they'll give you an indication where you may have challenges with running your property checking and where you may need more constraints or you may need to apply some kind of abstractions, certainly where you're going to struggle. Let's talk about assertions. So kind of related to the spec, you don't want to be putting assertions on lots of low-level structures. For one thing, it's down at the implementation. That's not where you want to be. For the second thing, if the RTL is changing, which it could be changing under your feet, your properties are going to be subject too much to those design changes. You're going to be rewriting properties as the RTL evolves. You don't want to be doing that. If you write if you write your properties at more at the specification level, then they're going to change a lot less. This second one is something we see quite often. So you have a function that you want to check, and you're going to write some properties for this. All too often we see people trying to cram in the complete description of that problem into the assertion language. So they're trying to write their SVA or their PSL to entirely check that one or several functions that they want to verify. RTL designers are very good at writing very efficient RTL, very good at being synthesized. So what we propose and what we suggest is actually you mix the RTL and simulation. So you write the modeling code. You try and remove some of the complexity out of the system Verilog. The tool has to synthesize the property. So now we can synthesize some RTL with the property itself, and you're more likely to get a result. Rather than an overly complex representation of the problem that's going to end in an inconclusive. This final one here is similar to the top one there, creating assertions too much on the internal signals. What we mean by this is you might have some RTL and it might have, say, I don't know, an FSM implementation. If you write some checkers around the FSM, then you may not capture the FSM misbehaving. You're going to capture problems of the FSM, but the behavior of the FSM might be governed by some higher level code, and you may not capture that the FSM is being incorrectly operated. The incorrect operation may not get caught within your low level property. So again, you should bring your properties up somewhat to a higher level. So the recommendation here is really that we should mix the RTL and the assertions to capture complex behaviors. Don't try and put it all in a property. Basically. Let's talk about doing assertions the right way. So the way we recommend you do it is actually to take the spec and to capture some information about the spec. Okay, so even before we think about writing properties here, so take the specification. Let's hope it's a good specification, and capture what it is you want to do functionally, what it is you're trying to verify, what it is this block does. Capture anything about the constraints. So how are we going to constrain this block? How are we going to constrain this design? What outside influences or assumptions are we making here that we need to reflect? And then set some coverage goals. So when do we know we're done, basically? And the way to do this, or one way to do this, is to start decomposing these functional checks. So you start with some higher level functional description, and then you start breaking this down. And you break it down into sub-functional requirements, and then further sub-requirements, and further sub-requirements, and so on and so on. These will generally be hierarchical, and they'll probably follow, to some degree, your design hierarchy too. So you may have some blocks in your code, and they'll reflect the kind of property structure. Basically, we're trying to drill this down into lower-level requirements until we get down to a level where we can actually write a property. Okay. So we've taken our high-level architecture spec and we've decomposed it down to such a level that then we now have something we can write in SVA or PSL. And there's two reasons to do this. One is that it makes writing the SVA then very simple, or the PSL, the property itself, very simple. It's based on some more simpler requirement. The other is there's now a relationship between, in our diagram here, P2.1, for example, and the architectural spec. You can trace it all the way down and all the way back up, which means you can now show that when you verify property X, it satisfies a requirement, or at least part of a requirement, further up in your specification. So it makes traceability easier. It means you can demonstrate your result to your reviewers, your management team, and so on. The other thing is, of course, if you solve low-level properties, once they've been proven, you can utilize that further up. To solve the slightly higher level properties and move up using the student guarantee kind of approaches. So the chances of getting closure on some of these higher level properties increases because you can verify the lower level behaviors. Simulate the constraints. Again, this is something Ashish mentioned, I think. So if you have constraints, run them through your simulator as well. It's good practice. Formal engines. So while you don't need to be an expert in all the vendors' engines or internal engines you may be running, it's good to at least have some appreciation of how the tools work with respect to engines. And the fact that, at least if you're new to this, formal is way different from simulation and how they work. So simulation is sequential in nature. It starts from a point in time and moves forward. And you run the same engine on multiple servers typically. Formal is concurrent. Okay, so it can work on lots of things at the same time. It has many engines. The tools these days have, a dozen or more engines. And you can run these on multiple servers. And you may run different engines on different servers. You may run different properties on different servers with different engines. You may even run parts of properties on different servers with different engines. So the tools can split these up. So one of the things we see customers often doing is just throwing all the properties at once into the tool and kind of pushing the button and hoping for the best. That may not be the most efficient approach. It can yield results. I'm not saying it can't. And we'll look at a little bit more of this on the next slide. You need to be aware of how the engines are working and ensure that no properties are getting starved during verification. Okay. So you need very efficient orchestration of the engines. In other words, the time shared between the engines, the resources shared between the engines, the heuristics built into the engines is all what the orchestration is. How well the engines are working between themselves and how they're working across your property set. So you need to use the right formal engine on maybe a few properties. So it's working out this balance. And again, I'll talk a little bit more about this on the next slide. This last bullet is, again, something we see all too often. So the designer was working on project A today, and they're running formal, and they spend some time tuning some engines, maybe working with their EDA partner, and selecting some engine sets, and they get some decent results out, okay, and they get good closure on this sequence of engine with these current engine settings. Tomorrow they come in and they're working on project B, and the first thing they do is they dig up the scripts they had for project A and they push the button and they run them again on project B. and they won't necessarily work the same as they did on Project A. The engines for Project A may be different from the engines required for Project B. And so all too often we see this coded into environments. And again, what you need is a very efficient orchestration here so that you can work out of the box each time with the tools to at least get a first pass of results, and then maybe start playing around with engine settings for those harder properties or those ones you didn't get initial closure on. So it's worth understanding where complexity lies in your design and in some of these properties to understand where the more difficult ones may be, and then you can partition your property set accordingly and make sure you go after the easy properties first because they can pay benefits into the more difficult ones. So this is part of the orchestration problem between engines. The way this typically works is that with an orchestration, as I said, the engines will have some heuristics built into them, or the tools will, in how they run the engines. And you'll have multiple engines. And they will run a pass 1 of several different types of engines, and a pass 2, and then another pass, and so on and so on. And these will be time-shared. They'll have various limits and measures built into them. And they may be some engines that are running pass 1 and pass 2, or they could be different engines. But what you're looking at here is several passes across different properties, and the different properties have different complexities. What you don't want to do is run and have the engine spend too much time on, say, P2 and P7, such that the simpler properties get starved of resource and they don't get solved. Okay? What you want is an efficient orchestration such that it can spend some time on all of them, but solve the simpler ones first. And then we can obviously use that to do fanning, cone pruning, etc., so that in pass 2 and pass 3 we can then hopefully make the problem simpler and go after some of these more difficult problems. Then we come to coverage. So there's a couple of different coverage items I want to talk about here. So we're talking here about design or property coverage, not completion coverage. But there's 3 here in kind of increase in order of complexity, if you like. So the first is assertion density, really easy kind of metric. You know, you're looking at here at just assertions per lines of code. So there's various kind of industry metrics out there. You know, number of assertions per 100 lines, somewhere between 1 and 10 typically. And these are typically reported very early by tools. In fact, you don't even need a formal tool to do this. You could do this in a linter, or you could even write some script to pull out how many assertions you've got per lines of code. But a very kind of rudimentary, basic, but you know, somewhat useful initial metric. The second type of coverage here is something we call MSD, or minimum sequential distance. So this is really trying to see if you have areas of design that are completely uncovered by properties. Okay, and we're looking at registers here. So we're looking at 2 things, and I have a slide on this. The next slide discusses this in a little bit more detail. This is really saying, okay, do I have any blind spots? Do I have any areas of my code that are completely uncovered by assertions? And so I need to go and fill those in. Or are there areas where I have very low observability and I may need to go and add some extra properties? So we'll talk more about this shortly. And the final one is cone of influence. So MSD you can look at straight after elaboration. So we don't need to run formal analysis here, but we need to build the model. Cone of influence is something that you get after the full analysis. So this is the ability to look at both complexity, but also what design logic is being pulled in by a target. So we'll have a property, and we're able to look at all the logic that was used or pulled into the fanning cone of that one target. So this allows you to see exactly what logic in your design is being covered by any one property, and therefore if there's anything that's outside of those properties. But again, this is reported after formal analysis. So the top one doesn't really require any formal analysis. The second one at least requires elaboration, and the final one requires you to run some proof analysis. So let's just look at MSD. So here's a simple illustration. So in the diagram on the right there, you can see we have an assertion where the red kind of cross is. What we're really trying to do is say, okay, get the tool to report how far away from the assertion in terms of sequential distance, okay? So number of flops, every flop is. So we can see here, this reg R2 is 1 level of logic away, reg R1 is 2 levels of logic away. So all you're trying to do here is say, are there areas of my code which are completely uncovered? Do I have any blind spots? Do I have any holes? Okay, so I've created a property set that I hope satisfies the function of this block. I'm just now looking, okay, do I have any holes? Do I have any areas where I should have assertions and I don't? Is there any logic that's hanging off? The other thing is of course, we're measuring the levels of logic here. So if it's 1 or 2 levels, you can argue quite easily that, you know, the behavior of that logic will probably get caught in that assertion. Okay, so any misbehavior will cause a firing. If we're at 10 levels or 12 levels or 15 levels away, you can probably argue that observability is pretty low. And so we probably want to go and scatter a few more properties around that area to try and increase the chance of finding a bug. So you can see down here, here's a chart at the bottom here, and you can see the various covers in the assertion MSD view and the assertion MSD graph view. You can see our resets and interrupts block has 0 coverage here, so we need to do a better job there, and some of the other blocks are looking pretty good. So for the last few minutes, I just want to switch gears slightly. So we've looked at some kind of the do's and don'ts of formal. But one of the things we find is that customers come to us and they go, okay, you know, we like the idea of formal. We think it has value. We have no idea how to start down this path. Okay, how do we start maturing our process so that we can take advantage of these new technologies, or at least new technologies to us? So I'm going to talk about this thing called the formal ABV, assertion-based verification capability maturity model. So this is a process reference model. It's something that Harry Foster created probably about 10 years ago. In fact, it's for those of you who have looked at the Verification Academy, the Academy is built on a simplified version of this. Okay, the Cruel WalkRun idea is based around this too. So Harry created this to help customers, help companies understand and organizations understand and assess where they were today in terms of their maturity and what value they could get by stepping through the maturity model and adopting different techniques. And we've used this with customers to do the same thing. Okay, so help them understand, okay, if I want to mature, if I want to go to the next state of maturity, how do I do that easily and what value do I get? And not only value would I get, but what infrastructure is required, what skills are required, what resources are required to do this. Okay, so this is the model. It's based on the standard kind of CMM, and Harry's just modified it to meet our means. So any of you familiar with the kind of CMM, CMMI stuff, this should look vaguely familiar anyway. So there's 5 levels. At the left-hand side, we got ad hoc. So this is the simplest. And then 5, we have optimizing. This is the most mature. Okay, and you may be in one or more of these categories too. So if you're looking at this as a company, you know, you could be in 2 and 3, for example. You needn't necessarily be in any one category. So at the 1 level, in terms of assertions, this is very ad hoc companies, okay? There's no company mandate here for using properties or assertions, even in simulation. Okay, you've probably got 1 or 2 heroes, individuals using some properties. They may even be using different languages for these, okay? It's completely uncoordinated. Level 2, we see there now is company mandate, okay? So the company is saying, okay, you will use assertions in your verification strategy, and those assertions are probably being used in simulation pretty widely. You've probably decided on a single language, so System Verilog or PSL, for example. You're focused on debug time and quality, and we see the start to use formal. So automated apps start creeping in at this level too. So it's slightly more mature. By level 3, we see a lot more focus on things like bug hunting. Okay, so not high levels of formal expertise here, because you're just taking properties, you're putting them into the formal tool, and if bugs drop out, great. But you're not looking for absolute proofs here, probably. So you're getting a lot of bounded proofs, maybe, but you're seeing good results from bug hunting, hopefully. By level 4, you're now targeting blocks of logic. You're saying, okay, I'm going to replace simulation with formal on some areas of my code. I'm looking for absolute proofs here. So this is really design assurance, gets kicked in at level 4. And then by level 5, it's really about optimizing, refining the process, measuring, controlling, the feedback loops are all in place, and the process is kind of complete. Just as an illustration to this, over the next couple of slides, I'm just going to talk about Oracle. So Oracle are a company we've worked with in the US over a number of years. And they precisely kind of followed this model. So they were a level 2 company. Okay, they were doing some assertions, some UVM simulation. They had no formal expertise. They were novices. They kind of thought, you know, we had this project and this rapid SoC development project, and they kind of thought, okay, you know, we can do a good job with simulation, but we think we can probably do a better job. And so they started thinking about what model checking can do. And so they talked to us, and the first things they looked at were clock domain checking. So the original formal app, if you like. So CDC's been around forever, so that's one of the things they started looking at. The other thing was interconnect checking. So they had low levels of expertise, but they said, okay, let's take a few apps and let's start plugging these in and see if we can derive any benefit. And even the interconnect checking, they were focused on some specific areas here. So interrupts and DFT signals, particularly around boundary scan, I think. And pretty soon they could see that there was benefit there. They were getting good results from CDC. They were finding bugs, fixing bugs, and the interconnect verification they could see was saving them a lot of time and giving high value. So they say, okay, you know, we think we can use model check and we think it can help us. So what's the next stage? So they were at level 2, moving through to a level 3. So now they started looking at some assurance techniques. So they said, okay, let's look at our design. There's some really, really very well-suited blocks of code here. And they weren't complete blocks. Some of these were, you know, buried inside other blocks that were less suited for formal. But they took some things out. Okay, they took some, or encapsulated some low-level blocks, arbiters, controllers, for example. And they started looking at writing properties for these and replacing simulation effort. So maturing through the flow. And then they came out at level 3. And they said, okay, this is great. You know, we're able to do all this, and our expertise is growing. The number of engineers that are running formal and running formal successfully is growing. There's a general belief in the company now that formal is valuable. What else can we do? So then they started doing bug hunting. So more and more engineers, more design engineers started picking up the tool and just doing bug hunting. And then, indeed, they took even more complex blocks and started running formal. And so, you know, moving through a level 4, and they're now a level 5 company. So they have formal in, they design for formal. When they're designing blocks now, they look at the architecture and they partition those blocks such that they can run formal on some aspects of those blocks much more efficiently. They mix simulation and formal. They plan for it now. It's in their test and validation plans. If you want more detail of the Oracle story, I've just scratched the surface here. There's a DVCOM paper. There's also some stuff on Verification Academy through the Verification Horizons newsletter. If you want some detail about maturing your processes, there's a section on the Academy website too. It wouldn't be an EDA presentation without a marketing slide. I'm not going to dwell too much here. But so Oracle were using CDC. They're using connectivity checking, auto checking. They're looking at cover checking and register checking now. And of course, they were using property checking too. So, summary. So hopefully this just, obviously just scratched the surface. But the aim was just to provide some initial guidelines and some, you know, some pointers, if you like, to our more novice users in the hope that they get successful. You know, we don't want them to become frustrated and revert back to simulation. We want them to be successful with formal. So hopefully these methods helped. The Oracle study shows that, you know, you can go from nowhere to a level 5 very mature formal company. It took about 3 years for Oracle to do this. So it's not an overnight thing. And I think it was 2 projects as well. And then finally, Joe Hupke, our marketing guy, runs this LinkedIn group. If you want to share any of your righteous tips, he's happy to hear of them. I think that was it.
Thanks, Mark. Thank you very much.